Okay, so as I said, we cover some basic topics in this course, but I want to kind of tie it in with the symbols and the algebra and the variables and stuff like that, so you can see that math is not a bunch of separate rules, that it really is one really small set of big rules that applies to everything. And that the trick is not learning new rules for everything, but seeing how these few big rules apply to numbers in different forms. So I take a different approach than most teachers do to pre-algebra. My thought behind that is all of you have seen this material before, and either you understood it the first time and you don't need to see it that way again, or you didn't understand it the first time and it would be frustrating to just see the same old thing again. So I'm going to try to show you something a little different. What I've found is that many of the problems students have in math come down to the most basic concepts, right down to the absolute most basic concept, which is also probably the most misunderstood concept in math, which is the idea of a number. If I can get my, there we go. What is a number? Well, if I put a 4 on the board, show of hands, how many of you would say that that's a number? Most people would. And some of us have even been taught that. But it's not a number. It's incomplete. That is just a numeral. It's an amount. To be a number, it has to tell us more than just how much, but it has to tell us of what. So if I have something like this, 4 cows, now it's a number because it not only tells me how much, but it tells me of what. So I call these two parts of a number the count, in this case, which is the 4, which tells me how much, and the name, which is the label, or tells me of what. What is it that I have 4 of? Now you might be thinking, is this another one of those teachers that's going to make us label everything? No, I'm not going to mark problems wrong if you don't put units on your answers on a test. But when I'm talking about stuff in the lectures, I am going to include those labels because those labels actually play a huge part in our calculations. To show you what I mean by that, let's take a look at the two most basic of math operations. Addition and most people would say subtraction, but the second most basic math operation is actually multiplication. Somebody might be thinking, well, what happened to subtraction and division? Well, subtraction is really the same operation as addition. It's just going in reverse. And we'll look at that more as we talk about integers and stuff like that. Division is the same as multiplication. It's just the reverse. We'll talk about operations coming in pairs, what we call inverses. One of them is just the reverse of the other. So for addition, let's say I take something like 4 inches plus 7 inches. How much do I have? 11 inches. Good. Nothing groundbreaking there, right? You guys could all do that walking into the room. Probably not quite worth your $300 for the course yet. But if we look more closely at these two parts of the number here and how they interacted in this calculation, let's look at the counts. We had the 4 and the 7, and we combined those to make an 11. We combined the counts. When we add numbers, we combine the counts using addition. But let's look at the names. We had inches, and we ended up with inches. When we add, we just keep the same name. We didn't do anything with it. But let's look at multiplication now. If I take those same two numbers, first of all, I'm going to abbreviate inches, IN. So 4 inches times 7 inches. Second, I'm going to use the dot for multiplication. Is there anybody who's not familiar with that dot for multiplication? It's the same as the x, only later on when we start actually using x as a variable, the dot makes it a little less confusing. So now, of course, 4 inches times 7 inches would be 28, but it's not going to be inches, it's going to be inches squared. If you think about it, if we're going to take 4 inches times 7 inches, generally we're looking at an area like that. So 4 inches times 7 inches would be 28 square inches, or inches squared. So if we look at what happened with our count and our name here, with the counts, we had 4 and 7. Well, we still combined them to make 28. So when we multiply, we still combine the counts. Only now, of course, we use multiplication to combine them instead of addition. The difference is with the names. Here we had inches, and we ended up with square inches, or inches squared. When we multiply, we also combine the names. Now you might be looking at that thinking that's really kind of a nitpicky thing to point out. But it has huge consequences when we look at our other forms of numbers. In fact, it even has huge consequences just looking at what numbers we can use in each operation. For example, let's go back here to addition. And let's take back to my 4 cows here. If I take 4 cows plus 3 boys, do I get 7 cowboys? That doesn't work out, does it? Or if I switch it around, 3 boys plus 4 cows. Do I get 7 boy cows? Of course, anybody with a farm background will tell you that this is a whole bunch of 4, right? Okay, I know it's a long way to go for a joke, but there's a good point behind it. I'm a math teacher, by the way, so I'm required by law to have a stupid sense of humor. You'll get used to it. There's a good point here. I cannot take 4 cows plus 3 boys. Why can't I add those together? Because when I add, I'm going to keep the same name, which implies that I must start with the same name. So if I take something a little bit more concrete, like 5 pounds plus 6 feet, when I try to add those together, what do I get? I get 5 pounds plus 6 feet. I cannot add them together because they don't have the same name. Now, sometimes I can change the names. Like if I have, 1 foot plus 7 inches. In some cases, I can change that from 1 foot to 12 inches, and now I do have the same name. 12 inches plus 7 inches will be 19 inches. So sometimes I can change the name so that I can add them. But when I'm adding numbers, if I don't have the same name, I cannot add them together. Now, of course, the same rule goes for subtraction since they're the same operation. For multiplication, however, if I take that 5 pounds times 6 feet, 5 times 6, combining the counts, is going to give me 30. But when I multiply, I also combine the names. So pounds times feet give me something called foot-pounds, which for anybody familiar with engines is a unit of torque, or in architecture is what we call a unit of moment. That's just fine. I do not need the same name to multiply. So you might be looking at thinking, okay, that's starting to get a little interesting, but still not worth my $300 for the course, right? Well, let's look at some different forms of numbers. Let's look at everybody's favorite number, fractions. I say that jokingly because I realize that if I surveyed students on their way in the door and asked them, what one thing do you hate most about math? 4 out of 5 students would say fractions. Most of the others would probably say the teacher. But anyway, let's see what you remember about these. What is this top number called? The numerator. Good. The bottom number is the denominator. Well, let's look at that more closely. What does it mean to numerate? Well, every 10 years, our government sends out people to do the census to numerate the population. What are they doing? They're numbering it or counting. The numerator is a count. Denominator. Well, we have different denominations of paper money, different denominations of churches and other organizations. To denominate means to classify or to give a name. People look at fractions and they see 2 numbers, but there's not 2 numbers there. There is one number with 2 parts, a count and a name. When I look at 2/7, what you need to see is that we have 2 of something. Just like we could have 2 cows or 2 inches or 2 feet, here we have 2 7ths. The 7 is a name. When we look at fractions, we'll go into more details to what that name of a 7 means. But for now, all we need to know is it behaves just like any other name on any other type of number. If I had 2/7 plus 3/7, well, somewhere around 3rd or 4th grade, our teacher told us that when you add fractions, first of all, you must have a common denominator. Well, that was not a special rule for fractions. Anytime you add 2 numbers, you must have the same name. It just looks different with fractions. So that was not anything new. It wasn't just because our 3rd grade teacher said so, but that's what we need for any numbers when we add them. That same teacher told us that when we add fractions, we add the numerators, the 2 and 3 make 5, and we keep the common denominator. Well, again, that's not just because our teacher told us, but that's how we add any number. For when we add any number, we combine the counts. 2 and 3 make 5. And we keep the same name. With fractions, it's keeping the common denominator. So the rules for fractions are not special rules as we were taught. They're the same rules we've had for any other form of number. Now, what if I have 1/4 plus 3/5? Can I add those as they're written? No, I cannot, because right now they have different names, 4ths and 5ths. When we hit fractions, we'll talk about how do we rename them so that we can add them. For right now, all we need to know is they have different names. We can't add them together as they are. But let's look at multiplication. For multiplication, if I had that 2/7 times 3/7. Going back to that 3rd grade teacher, they told us that when you multiply fractions, what do you have to do? Just multiply straight across, right? 2 times 3 is 6. 7 times 7 is 49. Again, that's not a special rule for fractions. That is the same as we would handle any number when we multiply. We would combine the counts. 2 times 3 is 6. And then we would also combine the names. 7 times 7. If we look at our 1/4 times 3/5, those have different names, but our 3rd grade teacher told us that when you multiply fractions, you don't need a common denominator. Again, that's just like any other number. We don't need the same name to multiply because we're going to combine the counts. 1 times 3 is 3, and then also combine the names. 4 times 5 is 20. Just like any other form of a number. Well, let's look at another form of a number. Let's look at a decimal, 0.21. Now, how would be the formal way of pronouncing that instead of just 0.21? Perfect. 21 hundredths. Good. And when we write it out that way, it's pretty obvious what's the count and what's the name. Our count, of course, is 21, and the name is hundredths. So if we go to do an operation with decimals, let's take our 0.21 plus 0.3. When I go to add those together, I usually set them up vertically. Can I just do this? Does that work? What's wrong with what I did there? Yeah, that same 3rd or 4th grade teacher told us that when we add decimals, the decimals got to line up. We have to do 0.21, and the decimal has to be right below it, so this is 0.3 like that. But why? 3rd grade teacher said so. Yeah. Okay, you're catching on right there. If we look back at these here, this is 21 hundredths, just like we had over here. This is 3 tenths. They don't have the same name. Technically, we can't add them together the way they're written. But fortunately, we can give them the same name really easy by just doing that. Now it's 30 hundredths. So now they have the same name. And once we've done that, the decimal points would have lined up automatically when we go to add them. But we can only combine things that have the same name. So now we would do 21 plus 30 is 51. And we're always taught the decimal point comes straight down, right? Again, that's not a special rule for decimals. That's because when we add numbers, we keep the same name. 21 hundredths and 30 hundredths give us 51 hundredths. Multiplying, however, do I have to worry about lining up my decimal point? No, because when I multiply, I don't need the same name. So I have 21 times 3 gives me 63. Where's my decimal point go? Oh, you go over 3. I got to put a 0 here and over one more spot to put my decimal point in. Well, why did I have to have 3 decimal places? Okay. That same 3rd or 4th grade teacher told us that when we multiply decimals, you go into the problem and you count 1, 2, 3 decimal places in the problem. You have to have 1, 2, 3 decimal places in your answer. But why? Well, we put a lot of faith in that 3rd grade teacher, didn't we? It's not just because they said so, but this is 21 hundredths, and this is 3 tenths. And when we multiply, we not only combine the counts, the 21 times 3 gives us 63, but we also combine the names. Hundredths times tenths would be thousandths. So when we're counting up those decimal places in the problem and putting that many decimal places in our answer, all we are doing is combining the names. All these special rules and shortcuts we were taught for fractions and decimals and other forms of numbers are just nothing more than whether we combine the names or have to have the same name to start with. Let's look at one other form of a number before we take a little break. This one. Some people get a little queasy when we throw the letters in with our numbers. 4x is an algebraic number, but it behaves no different than any of our other numbers. What makes a lot of people nervous is, we compare the 4x to the 4 cows or the 4 inches or 4 pounds or whatever. people look at this and we know what a cow is and we know what an inch is, so it makes us feel comfortable. When we look at 4x, we don't know what x is, but it doesn't matter. It still follows the same rules. If I had 4x plus 7x, well, just like 4 inches plus 7 inches up here, I'm going to get 11x. Good. Because I combine the counts. 4 plus 7 makes 11. And I keep the same name of x. Well, what if I had 2x plus 5y? What do I get? 2x plus 5y. Good. Just like having the 5 pounds plus 6 feet, I have different names. I can't combine them. The same here. I have x's and y's. They're different names. I can't combine those with addition. Multiplication, on the other hand, 4x times 7x. I'm going to combine the counts. 4 times 7 makes 28. And then just like inches times inches gave me inches squared, x times x gives me x squared. Or if I look at my 5x, and we'll go times 2y instead of plus. I'm going to combine the counts. 5 times 2 is 10. And then just like feet times pounds became foot pounds, x times y becomes xy. When I multiply, I also combine the names.
The question I have is 4x times 7x. We have 28x squared. That's just because we had the two numbers?
Yep.
We'd have three numbers and it would be
X cubed.
x cubed.
Yep. Yep. And we'll go over that more when we talk about variables specifically. But yeah, you can give powers on there that change how they multiply and add and stuff like that too. A lot of little things that come into that. But that's just an introduction to kind of all these little rules you're taught and how they do tie together. Don't worry, this was a lot of stuff in a half an hour's time. We're going to spend the next 5.5 weeks picking this apart and going over the pieces in more detail. So I'm going to take our first break right there.